integration by parts. And basically, this is just applying the product rule in reverse. So here we have the product rule. Okay, so product rule. The derivative of the product of two functions is equal to the first function times the derivative of the second one, plus the second function times the derivative of the first. Okay, that's the product rule when you're taking the derivative of a product. If we take integrals of everything, then we get something like this. So taking the integral of a derivative just gives us back the original, and then integrals of this and this. And then we take this formula and we solve for this one right here. So in other words, take this other side, and we have the integration by parts formula, okay, which is the integral of u dv, which is this piece here, is equal to uv minus integral of v du. Okay, so that's how that works. That's the formula right there. Now, how to do it? First thing you have to do is you'll have a problem like this, but you don't know right off the bat what's your u and what's the dv. Okay, you don't know what's the first function and the derivative of the second function. You don't know what that is at the beginning. But after some experience, you figure out how to do it. This one thing that helps, but it doesn't like solve all your problems, is when you have is to do this priority, because logarithmic functions, inverse trigonometric functions, algebra, that would be like a polynomial expression or something, or like a rational function or something like that. And then trigonometric functions and exponential functions. This goes from order from the one that's most changed into something to the one that's least changed, because the key is this u right here. Instead of having to take the integral of that, like for example, logarithm, that's really hard to integrate. But if you take the derivative of the logarithm, you get 1 over the function, which is easier to integrate typically. And same thing with these other ones. Whereas exponential, when you take the derivative, it's not going to change much. So it's really not going to help you that much to make u be the exponential function, okay, if you have other things in play. Okay, so that's the first one. Choose your u, then identify your dv, which would be the rest of your problem, including the dx or whatever variable you're integrating in. And then you calculate du and v. And then finally, you calculate the right-hand side of the equation, okay? So let's do an example. Exercise number 1. So here's the steps again. We'll do an example. So here we have a trigonometric function right here, and a algebra. Okay, is what you'd consider those. So the thing to do would be to let u be the x part. So u would be this one, because it's higher priority than the trigonometric one. And so then dv would be the rest. So cosine of 8x dx, like that. Okay, and then you calculate, so we identified dv, and now we calculate du, and we calculate v. So du would be the derivative of this, which would be dx. The derivative of x is just 1, so 1 dx. And then dv, we take the integral of this to find our v. And let's see here. If you take the derivative of sine x, you're going to get cosine eta, sine eta. The integral of, if you take the derivative of sine 8x, you're going to get cosine 8x times 8. So we will put in 1/8 there to counter that. Okay, so we have everything. So we did step number 2. And then number 3, we calculate that. So this integral, we've identified this as u and this as dv. So uv minus the integral of v du. And so just put the u and the v in there. So here's u, there's v. So that's going to be x over 8 sine 8x right there. And subtract v du. So v is this one. And then du is just dx. So it's 1/8 sine of 8x dx. Okay, now here, the integral is going to have a cosine 8x in there. If you take the derivative of cosine 8x, you're going to get negative sine of 8x. So we will change that to a plus so that when we take the derivative, we'll get negative. But then you'll have another 8 coming out, so we'll have to divide by 64 to counter that. Okay, so when you take the derivative here, you'll have an 8 coming out. The 8 will reduce that to a 1/8. And then we put a constant on the end, and that is going to be the answer right there. Okay, so that is a typical integration by parts problem. Let's do some more examples. Number 2, and here we have a logarithmic function. Okay, and so according to this priority, logarithms are first because it changes by quite a bit. So we're going to make that be the thing. Now the square root of x can also be written next to the 1/2, which the 1/2 can come out in front. So really we're going to have 1/2 log of x. It's easier to put like that. Okay, then dv can just be is everything else, which is just this dx. Okay, so du will be the derivative of this is 1/2x, and the integral of this one is just gives us back an x. Okay, we don't have to put plus a constant or anything. We put a plus a constant on the very end of the problem, but not at this point. Okay, so I've identified all that. We've calculated those. Now we calculate it. Okay, so u is 1/2 log x. V is x. And we have x here. Du is this one right here. I forgot to put a dx right there. I guess it doesn't matter that much, but the technicality. So here this is x over 2 log x. Of course, the x's here cancel, and we just have the integral of 1/2. So that's going to be minus 1/2 x when you take the integral plus a constant. Okay, so that's the basic idea. Any questions about how to do this at this point? This is another important thing is recognizing when you can use this, and I guess that will come later. So just have you practice with a bunch of these. The more of these that you do, the better, because then it helps you to train to figure out when you can use this and when you should use something else. Okay, so this is another one, but this is a little bit more difficult here. So remember LIATE. You've got a trigonometry, and you have a exponential. So we'll let u be the trigonometry part, and dv will be everything else. Okay, so now du is going to be cosine. You have a 3 coming out, 3 cosine 3 theta, and then d theta, and then dv is, no, I'm sorry, it's going to be v. Taking the integral of this, that's e to the 1/2 e to the 2 theta. Okay. So we go ahead and plug everything in. U is sine 3 theta, and V is 1/2 e to the 2 theta, and it also appears here, so 1/2 e to the 2 theta, and then du was all this, so there's a 3 there, cosine 3 theta. Okay, now here, you probably can see right now that this right here is this integral that's kind of similar to this, okay? Because cosine and sine are kind of similar with each other, and so if you haven't seen something like this before, then you probably be thinking, okay, we ran into a dead end here. This is not going to work. The integration by parts is not going to work. Okay, that's very common to have that feeling at this point. However, a very interesting thing happens. Let me just show you. So we did this problem using integration by parts. We'll do this. We'll take just this integral. I'll ignore the 3/2 for now. We'll put that in, but we'll put that back in later. But let's look at this problem right here without the 3/2 or the minus. And we'll use integration by parts to do that. So we just do the same thing. So letting u be, this time it's cosine of 3 theta, and dv will be everything else. So du becomes -3 sine 3 theta, and v becomes e to the 2 theta over 2. Oh, and this is, I keep on forgetting to do theta. Okay, so that's u times v minus integral of v du. So the u is cosine 3 theta, and the v is this one. And here we have what e to the, and then du is -3 sine of 3 theta. So that's going to be plus 3 sine of 3 theta d theta. Okay, so now at this point, it appears, because right here, our original problem was to find this integral. But in order to find that, we need to find this one, right? But then, according to this, it seems like in order to find this one, we need to find this original one. So it's like, well, if we could just find the original, if we could find this, then we could find itself. So that's kind of like, well, okay. However, what you do at this point is this. You plug all of this into here, okay? And you rewrite this whole formula here. Okay, so this formula is the integral of e to the 2 theta sine of 3 theta d theta. equals, and then there's this part here. So that's what? Sine 3 theta, e to the 2 theta, all over 2, minus 3 halves. So there's minus 3 halves, and then it's the integral of this, which is right here. So all of this goes in right here. Okay, so what we're going to do is we're going to distribute the 3 halves in. Distribute into here. So that's going to be minus 9/4. And instead of doing dittos, I should just write the whole thing out. Okay, now what I want to do is I want to take all of this. So I take all of this to the other side of the equation, and I combine it with this. When you combine those together, so you're adding 9/4. This is like 4/4, right? So you're adding 9/4 with 4/4. So if you add this to both sides, if you add 9/4 of this to both sides, you're going to get 13/4 of the integral. And then over here, you're going to have e to the 2 theta sine 3 theta all over 2 minus 3 e to the 2 theta cosine of 3 theta over 4. And then you multiply both sides by 4/13 to get rid of that, to get rid of this. And that gives you let's see, 4, so that'll be 2 e to the 2 theta sine 3 theta all over 13 as you distribute that in, and then distributing here, the 4's reduced. You get minus 3 e to the 2 theta cosine 3 theta over 13. And then we'll tack a constant on the end. We could have been carrying constants all along, but I'll just tack that on the end. And so that's the answer right there. Okay, so there's that one there. Number 3. That was done kind of an interesting way. Number 4 is also kind of an interesting problem. Here's where things sort of fall apart as far as here's why the LATE rule doesn't always work. It's not going to work in this case because if you're looking at algebra, if you set u equal to 5x over 1 plus 2x squared, then that's just not going to work out very well. Okay. Because when you take the derivative, it doesn't get any easier. It just gets really complicated derivative. But this one, well, I don't know what intuition to tell you, but it does work if you make u be 5x e to the 2x. So you look for v to be something, or dv. You can look for u to be something that like gets easier when you differentiate it, or you can look for v to be something that gets nicer when you integrate it. And this 1 plus 2x to the negative 2, which is like 1 over 1 plus 2x squared, right? Which is this part right here, dx. This gets easier when you integrate it. That's the key to this problem right here. Okay, so du, we need to use the product rule here. So that's 5 e to the 2x plus, that's the derivative of x, which is 1 times this part, plus this part, the 5x, times the derivative of this, which is 2 e to the 2x. So that's going to be 10 x e to the 2x. And that's all multiplied by dx. Okay, and then this one, when you integrate this, it gets easier because you get 1 plus 2x to the negative 1, or negative of that. Because when you differentiate this, you have a negative coming down, which cancels that negative. And then this reduces by 1 to give you a negative 2. Oh, and then there's a 2 that comes out, right? So you'll need a 1/2. Yeah, to counter the 2 that comes out of here. And you take the derivative of 1 plus 2x, which is 2. Okay, so now we can go ahead and plug everything in. So this is u v minus the integral of v du. Because of this part right here, I kind of think of this as you're doing voodoo, something like that. Okay, but anyways, 5x e to the 2x, and then v is this one right here, negative 1/2, 1 plus 2x, minus the integral of v du, so it's the product of those two, this times this. Now, the interesting thing, before I put that in there, I'm going to, if I factor a 5 e to the 2x out, an interesting thing happens. I get 1 plus 2x. Okay, so I'm going to put that in as, so the du part is going to be 5 e to the 2x, 1 plus 2x dx. And this part right here, that minus will flip that sign, and the 1/2 will go here. The rest of it, this right here, goes in. This is 1 over that. So this is 1 plus 2x. And so what makes this one work out really nicely is that these are going to reduce. Okay, and so that becomes something that's much easier to integrate. So what do we got here? We have, this goes into the denominator, so that's going to be, we have the numerator will be 5x e to the 2x. And the denominators that we have, it's going to be negative. And the denominator is going to be 2 times 1 plus 2x. Okay, and then this piece right here, what is that? The integral 5/2 e to the 2x dx. So e to the 2x seems to be the one. Now when you take the derivative here, you're going to get a 2 coming down. So we'll change this 2 down here to a 4. That way when the 2 comes down, it will reduce that to a 2. So at the beginning, here we have an integral with limits on it. And let me just kind of show you how to handle that. So at the beginning, we talked about, or I mentioned that this also works for definite integrals, okay? Now, when you have these limits right here, when you do the definite integral, you need to, on the UV part, so this is the UV part, you need to tack the limits onto there, okay? So you can like just take the integral as if, just like with normal definite integrals, one way to do it is just do the definite integral. Just do the integral without thinking of it as a definite integral, then tack the limits of integration on later, and then integrate this, and of course tack those on later after you integrate this. Okay, so that's kind of how that works. So we'll go ahead and do this problem here. And this one right here, I'm going to show you a different way to do this that's not integration by parts. So the standard way to do this, which probably every calculus book would show you to do this using integration by parts. But there's also something else called another way that they show you how to do it, which is probably more like what I'm about to show you, but not quite exactly. So here's how I would tackle this problem, okay? Rather than using the integration by parts, because if you use integration by parts, what's going to happen is it's a lot of like finding u, dv, and all this other stuff, and that takes quite a while. And you'll have to do that twice, because the first time that you do that, this t squared, you'll let u be, so what'll happen is you'll let u be t squared, so your du will be 2t and dt, and then the v dt will be like cosine 2t times 2t or something like that, okay? And then so then you'll have to do it again, and by letting u be t and then dv being the rest, and then so you have to do this twice if you do integration by parts. Okay, but what I do is instead of doing that, I guess what the integral is. So guess, this is maybe guess and adjust. Maybe we'll call that the guess and adjust method. Okay, so here's what happens. If I take the derivative of cosine 2t, I'm going to get -2 sine 2t, okay? So if I do this, when I take the derivative of cosine 2t, I'm going to get negative sine 2t, but there's the sign, the negative reduces there, and I'll have a 2 coming out, which will take that 2 out, okay? So that means that if I differentiate this, this is a product, it's this times this, right? Okay, so if I differentiate, I'm going to get 2 pieces, okay? So the first piece will be the derivative of this part times this, which is going to be t squared sine of 2t, okay? And that's exactly what we need right here. That's exactly what we have right here, okay? Those are equal. So this part is, I'm trying to draw a smiley face, but it's just not working out. This is good, yay, this is nice, okay? But I also get the derivative of this times this, right? So I'm also going to get, okay, the derivative of this is 2, a 2 comes down, but that cancels that too. So it's going to be t cosine of 2t, like that, okay? So this is not good, okay? This is part, so that means that this is not the integral of this. But And this is where the adjust part comes in. Adjust. I can look at this piece here, and if I take the derivative of this, if I take the derivative of sine t, I'll have a 2. It'll be 2 cosine 2t. Okay. So now, if I take the derivative of this, okay, the derivative of the second part will be cosine 2t times 2. The 2 will reduce that out. So I'll have plus t cosine of 2t. Okay, but I'll have another piece, which is the derivative of this part, which is 1/2 sine 2t. Okay, now this and this will cancel out. So the reason that I chose this piece was because this gives me a piece that cancels that off. So those are going to cancel. If I take the derivative of this whole thing, these pieces will cancel. But I get this piece, which is not so good. However, that's not a big deal because I can just take down a derivative of this. Which is that. Okay, so now if I take the derivative of that piece, I have the derivative of cosine is negative sine, but I'll have a 2 coming out, so that'll be minus 1/2 sine of 2t. And those will cancel. Okay, so that means that all of this, that means this is the integral of that. And I just need to evaluate that from 0 to 2 pi. Okay, so I plug a 2 pi in first. And that's going to give me negative 2 pi squared over 2. Cosine of, I'll put it 2 pi, that's going to be cosine of 4 pi. And then here it's going to be 1/2 2 pi sine of 4 pi plus 1/4 cosine of 4 pi. And then I plug in a 0 and subtract. Like that. And sine of 4 pi, that's 0. Of course, these are also 0. Here we get 4 pi squared, but there's divided by 2, so that's 2 pi squared. Cosine of 4 pi is 1. There's also the negative sign there. Here, this is also 1. And this is also 1. So, but there's minus 1/4. So in the end, we end up with negative 2 pi squared. There's the answer. Okay, so in the summary, this right here is the guess part. Wait. Guess, and then this is adjust. They're just like looking at this right here and trying to adjust to make it turn out to be the integral. Okay. Number 6. Here we have, if you look at LIATE, the second one is inverse trig function, which is what we have right here. We have the inverse tangent. Okay, so well, let's let U be the arctangent of 1 over x. And so then dv will just be the dx. Okay, so du will be the derivative of this. So recall that the derivative of the inverse tangent is 1 over 1 plus x squared, right? So I'm just using this formula here, which is the arctangent is the same as inverse tangent. It's just written differently. Okay, so this will be 1 over 1 plus, this is a 1 over x instead of an x though, so it's 1 over x squared. Okay, so I'm just plugging into here. I'm just plugging the 1 over x into here. Then we need to take the derivative of this part. Okay, now, and it's going to be negative 1 over x squared, but let me show you just in case. So 1 over x is the same as x to the minus 1. So when you take the derivative, you have negative 1 coming down, and then to the net minus 2. And then that's negative 1 over x squared, which is right here. And then, of course, that's times dx. Now, probably what you want to do is you want to take this and multiply by x squared over x squared, just to get rid of the complex fractions. So that becomes negative 1 over x squared plus 1 as you distribute these x squareds in. Okay, and then v is just going to be x because it's taking the integral of dx gives you x. Okay, great. So we'll call this I for integral. And so at this point, we have the integral is equal to, we'll go ahead and go u v, but you're going to evaluate from 1 to the square root of 3 minus the integral from 1 to the square root of 3 of v du, voodoo. Okay, so the u is, again, this part right here. And the v is x. So u there, v right there. And that's going to be valued from 1 to the square root of 3. And then this part is going to be v du. So that's going to be this times all this. dx. So the v is this part, and the du is the minus 1 over x squared plus 1. Okay, let's see here. So we'll have this piece, and then we have minus. Well, it's a minus, so we'll go ahead and make it a plus. Here, you can just use a substitution, maybe x squared plus 1. Use substitution x squared plus 1. And then what's going to happen is you'll get something like this. If you take the derivative of this, you get 1 over that times 2x. Well, there's the x. And the 2 gets reduced with this one. Okay, so the derivative of this is this. Okay, so let's go ahead and put everything in. Put the square root of 3 into here. Subtract and put the 1 in. Put the square root of 3 into here. Okay, root 3 squared is 3 plus 1 is 4, so that's going to be 4. Put the 1 in. 1 squared is 1 plus 1 is 2. So let's see here. The inverse tangent of 1 over square root of 3, that's going to be an angle. And this angle here has, if you draw an angle right here, the tangent is going to be 1 over the square root of 3. This is pi over 6. Okay, so this is pi over 6. And inverse tangent of 1, that will be where you have 1, 1, root 2. This is pi over 4. Okay. So this one's pi over 6 from here, and this is pi over 4 from here, this angle here. And then right here, what do we have here? We have, you can simplify this a little bit if you want. 4 is 2 squared. And this 2 will come down. Okay. This 2 comes down, so that cancels. So you have log 2 minus half log 2, which is going to be half log 2. Okay, so in the end, the final answer is going to be root 3 pi over 6 minus pi over 4 plus 1/2 log 2.